So for the first one, what I found most interesting is I developed that whole bungee jumping lab largely because in your pre-assessment, your like what do you know survey and stuff, I felt like you guys didn't have any concept of elastic potential energy. It's the thing you haven't talked about yet. So you had lots of ideas about gravitational. And then after doing the bungee jump lab on this FIP, you all completely forgot about gravitational and you were all about elastic. So it was kind of funny. A few of you connected all the dots, and I was thrilled and really got, I think, even like went beyond what the book had done with thinking in terms of that potential energy. So you've got a bungee jumper, you apparently, and the unstretched length of the bungee is 10 meters, the stretched length is 42, and you are standing 55 meters above the Beaver River, which is just crazy. The one that is at Beaver? It's what? We are looking at total potential energy here. So what you have to remember is that there are two forms of potential energy. You have potential energy elastic and you have potential energy gravitational. So if we look at the elastic piece first, which you guys are really good at this point after doing the bungee lab, we know that it is equal to 1/2 k x squared, delta x squared, and that delta x distance is the distance between the stretched and unstretched length. So, and you guys did a good job with that. A few of you, oh, actually that was one of the issues. Some people forgot and used that 42, which is the stretched length, and it would have been perfect, except for that. So remember, it has to be the difference between stretched and unstretched. So it was 32 meters. And K, the spring value of the bungee, spring constant of the bungee was given as 65 newtons per meter, and then the delta X was 32 meters, that's squared. So you get a potential energy elastic of 33,280 joules. And that would be in the upward direction. So we'll look at where that plays in, and we'll revisit the sample problem your book had. And I was really impressed with the way some of you handled that. Okay, let's look at the gravitational now. Okay, so if we look at the potential energy due to gravity now, remember that the question asks at the moment that you stop falling. So at the moment you stop falling, you are there, which leaves you 13 meters above the river. So potential energy due to gravity, we know, is mass, height, gravity, and it's how much farther you can fall, basically. So we said that your mass, we said belatedly, but we did say your mass was 50 kilograms, and I already went back and edited the quiz for next year. Your height above the river is 13 meters, and of course we've got gravity, we've got gravity at 9.81 meters per second squared. And, you know, some questions about how to handle, you know, if we leave this as a negative, then I'll show you what we get, and it makes perfect sense. So, using that, we get a potential energy due to gravity of 6,376.5 joules, and that would be downward. So a negative sign there makes perfect sense because the energy is the ability to do work downward because it's gravitational energy.
Wouldn't the height be downward, though?
Pardon?
Wouldn't the height be downward, like -2?
Well, that's a good question. So, you know, I don't have a good answer, unfortunately. If we want to account for, and that's where I'm going next. So you can look at that height as a downward change in position, but if you're looking at it as a displacement, it's definitely a downward displacement. If you're looking at it as a height, it's a positive. You know? So I don't have a great answer for that. If we do that and we get rid of this negative sign, you know, what we have is the magnitude of the energy. Now this energy is definitely directed downward. The direction of work that could be done is downward. So what your book did on the similar problem to this, and this is just like the sample problem that we did together from page, I forget what. Your book said, well, total potential energy, and it added those two together. And at the time, we discussed that that seemed wrong. Because in one instance, the potential energy, the potential to move you and to do work is upward, and in the other it's downward, and it feels like they should be subtracted. And so I was really thrilled. If you do what the book did, you get, after sig figs, with a total of 39,700 joules. But I think that's disingenuous. And I think that the better answer is accounting for the fact that they're in opposition. It would be 27. Whoops. No. 26,900 joules, and it would be upward. And that's just accounting for the fact that that's the net. And maybe that's, maybe that's the difference, total versus net. Yeah, it would be. So the total potential energy is this. But this would be the net potential energy. Because they're in opposition, you're recognizing the fact that one has the potential to do work up, one has the potential to do work down, so it makes more sense to think of it that way. Is that clear? I would say about half of you went ahead and went with this net number, recognizing the fact that they were in opposition to one another. Well, on the test, what I think would be most, because you will have a problem like this on the test. What I think is most reasonable is to show the two and then almost write a little blurb that, the total, if they're added together, is this. However, the net potential energy that's there, the actual potential energy where the body, the jumper, could actually move is 26,900 up. So, okay. Hold on. So if we look at total potential energy the way your book did in the sample problem that was very much like this, they said, okay, well, you just add these two things. And when we just add those two things after sig figs, we get 39,700 joules. And there's no direction because they're in opposite directions, so we can't even designate a direction. This is just total potential energy. If we think about it in a way that I think is really more reasonable and appropriate, and we recognize the fact that the potential energy for one, the ability to do work, is upward. The work that could happen on you is this direction, and with the gravitational, it's this direction. Then that really, I guess, really comes more down to net rather than total. And that would be also adding them, but recognizing that one of them is negative. Recognizing that they're in opposite directions. So in essence, you would be subtracting them. Though we can fool around with that with signs. So when we do that for a net, we would get 26,900 joules, and it would be upward. Because the actual motion of this person, this physics student, is going to be upward. And if you think about it, if the gravitational potential energy was larger than the elastic potential energy, they wouldn't be stopping. They'd have a problem. They'd be continuing, past the physical limits of the band, I think. But it's an interesting question to ponder if you're ever going to go bungee jumping. I'm never going to go bungee jumping. But it makes for great physics problems. So yeah, I would say on the test, you might want to make this distinction. Because so what you're looking at here to get that 13 is how much further they can fall. So height above 0 point. And we typically use the ground or the water or whatever as the 0 point.
So that's what it is when it's all stretched out?
Yes.
So when they jump, how much farther will it go?
Well, it's because it says at the moment you stop falling.
Yeah, that's what I
So
thought.
yeah, the bottom of this chord is where you're going to stop falling and you're going to start to rise back up. And so at that very point, if there was no bungee, how much further could you fall? Because we're really treating them as separate things. The gravitational energy doesn't relate to the bungee in any way. It just relates to their position in space at that moment in time. Does that make sense? Okay. All right, so now we've got another, this is a mechanical energy problem, initial and final. And so we have a parrot with glasses, and the bird is flying 3 meters above the backyard at 15 meters per second, drops the glasses. How fast will the glasses be going when they crash into the yard? And of course, then we could do a whole other problem about the force on the glasses and how much force it takes to break glass, but I have a feeling you're getting new glasses. So if we look at this strictly as an initial and final mechanical energy problem, the initial mechanical energy is, or the final mechanical energy is the final gravitational plus the final kinetic, and that should be, assuming no loss to friction or anything else, the initial gravitational and the initial kinetic. So final gravitational is going to be mass, gravity, final height. Final kinetic will be 1/2 mass, final velocity squared. Potential energy initial is going to be mass, gravity, initial height. And the initial kinetic will be 1/2 mass, initial velocity squared. So there's only one of these that we can zero out, and that's the final. And most people did pretty well on this because it was something we had just done. So the final height is 0 because they crash into the ground. So we know that that goes to 0 immediately. Everything else is pretty much up for grabs, and what we want to solve for is that. The most common mistake on this was algebra. So 10,000 painted blue picked screaming algebra. So how do you know which of those you can cross out? You have to think about each of these. So, is any of these 0? And if it's 0, you can cross it out. Is the mass 0? No. Is the gravitational force 0? No. Is the final height 0? Oh yeah, it is. And obviously mass is never 0. Is the final velocity 0? No, then we can't cross it out. Is the initial height 0? No, we can't cross it out. In some cases, the initial velocity is 0 if we have a stationary object that's falling, but in this case it isn't. So we can't get rid of that so easily. Okay, so we know we've zeroed that now, and we're solving for final velocity. So it's just rearrangement, and so we get, and I'm going to do this in sort of one big giant step, 2 times mghi plus 1/2 mvi squared all over m, and then to get rid of the squared, we're just going to cut that. The place that people made an algebra mistake on this was they took this 2 and they wiped out, how did they do that? They wiped out the half, but then they forgot to multiply this part by 2. That was a really common algebra error. So, well, and if you're prone to that sort of, that's just a klutzy thing. It happens. So I tend to actually just kind of leave it. But that makes, and you can then get rid of all the masses, so you don't even need the mass. Okay, so I did go ahead and I got rid of the half, but then I just multiplied the front part by 2. I treated the 9.81 and the 3 both as negatives. Obviously, we can't end up with a negative under the radical. So what we get for a raw answer is 16.848143 meters per second. And we can have 3 sig figs because the mass cancels out. You didn't use it. So 3. So final velocity is 16.8 meters per second. Questions? Okay, so in number 3, this is a throwback. This is just a work problem. You got a 55 kilogram box on a ramp, 24 degrees above the horizon, being pulled up the ramp by some poor schmuck. And the first thing it asks you to do is draw the situation, label all forces and displacements. So in order to do that, we don't have to label the magnitude necessarily, but we need to put in the normal force, gravitational force, the force of kinetic energy, or force of kinetic friction, and the force of the puller. And that's going to look like this. Okay, now of course I did it in pretty colors because I can. You couldn't because you just had pencils. So we've got the box, we've got it sitting on the ramp, we've got normal force, gravitational force, force of the puller, kinetic force, and of course gravitational force is split into a y and an x component. So the work, part A is just work done by the puller, and that's just the force of the puller. Okay, so the work done by the puller is just the force the puller is exerting times the distance that the puller is pulling the object times cosine theta, and this is where most people made their mistake. That theta is the angle between the force being applied and the motion of the object. So it's not the 24 in this case. In this case, it's 0. It's cosine of 0 because the puller is applying force in the same direction that the object is moving. So that's the key piece. And then what that gets you, is 178 newtons times, we're told 7.5 meters, which I guess I should have labeled here as a displacement, and times cosine of 0, which is of course 1. So we get a work done by the puller of, raw answer, 1335 joules. Work of the puller with sig figs is 1300 joules because that's 7.5. So that was really easy. Most people got that. Okay, so in B we're doing the work done by gravity. And so we have to look at the motion of the box, and we have to look at the force. So this is going to be force of gravity. There are two options here, and we talked about this when we started this chapter, in terms of finding that cosine theta thing. So your book claims that it's always cosine of the angle between the force and the motion. But in this case, it's actually sine. And that's why I said early on, I think it makes more sense to look at the situation, look at the force being applied, and figure out which component of that force is on the same axis as the motion. And in this case, it's the x gravitational force. That's the only part of gravity that's on the same exact axis as the motion. So that would be f of gx times the distance the thing moves. And then if we look at cosine theta, where this is the angle between the force of gravity on the x and the motion, what is the angle between the force of gravity x and the motion of the box? 180. 180, because the force of gravity is in the opposite direction. So the force of gravity is this way, but the motion of the box is this way. It is 180 degrees between the two of those. Does that make sense? What do you mean? Well, because force of gravity x is actually force of gravity times sine. So what we've done instead of, what your book would do is just take, mass gravity sine. But mass gravity sine gets you force of gy, and we don't want that. So I think it's easier to look at it in terms of which part of the force is actually on the same axis. Use this, but then you still have to look at the cosine of the angle between the force and the motion. And here they're in direct opposition. What's the cosine of 180? -1. So it's just telling you that the work that gravity on the x is doing on this object is in opposition to the motion. It's negative to the motion. So it's, in essence, slowing it down.
So the work would be negative.
Yes, the work is negative. So we have this, mass gravity sine 24 times the distance the box moves times cosine of 180 because that's the angle between the force and the motion, force of gravity. So what we get is negative 1645.9 blah 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 joules. Well, with sig figs, negative 1600 joules. Unfortunately, of course, because whoever wrote this stupid quiz screwed up and the force of the puller obviously needs to be larger. I really need to fire my quiz writer. Yeah, I got to fire my quiz writer. Sorry. I'll get right on that. I have already edited this for next year. Yeah, this would mean that the puller was getting dragged down the ramp. I found this error in the key, I'm sure, and then went, oops, I'll edit that for next year, and never edited it for next year. So this time I edited it that day as I did the key and realized there was a problem. Okay, so yeah, this is, and you'll have one like this where you have a couple different forces acting on something. Find the work done by each force. This is similar to where you found the work done on the flour bag by the bungee. You're looking at just the force of the bungee. So remember, when you're doing work done by a specific thing, it's just the force of that specific thing. It's not the net work. You can do net work, and then we can get into kinetic energy theorem and all that. But questions, comments, concerns?